Okay, welcome everyone. My name is Tomi Yamamoto. I am the Assistant Director of Academic Planning and Student Affairs. Thank you for joining us today for our Admitted Student Information session. We're excited to welcome our second cohort into the Statistics and Data Science major this upcoming fall semester and hope to share with you today information that may help some of you make a decision on your admission offer, or for those of you who have already accepted your offer, to support your decision to join our new program. We'll start today's session with Dr. James Scott, who played a key role in the creation of this major.
Thanks, Tomi. How's my audio? Is all right? Good deal. Okay, well, welcome everybody. It's a delight to see such a number of people here. And as Tomi mentioned, this is going to be our second year, still a very, very new program, but it's so real having students on campus now that are actually taking this major in a way that it hasn't been in planning for a very, very long time. We're going to come to some of the nuts and bolts of the degree program later, things like what courses you take and what sequence do you take, how do you get advising, what's the career service, all that kind of logistical stuff. What I thought I would do here is rather than cover some of that stuff, I would kind of take a step back and think a little bit more about like what are the intellectually, like what is there to get excited about in this major? So let me just share some slides right here. Actually, I'm going to redo that because I want to make sure that I can actually share the audio as well. So I have one just short little video here. Okay, so what are you going to learn to do in this major? Well, there's a ton, right? I mean, there's obviously many, many classes that you'll take, both in our department as well as supporting materials outside in departments like mathematics and computer science, places like that. But if I had to kind of put a really, really short summary of what it is that you learn to do in a statistics and data science major, it would be these 3 bullet points right here. And this is a massive oversimplification to be sure, but basically you learn to describe data, you learn to make predictions using data, and you learn to make inferences about cause and effect. So what do I mean by all of these things, and how do they kind of fit together? I like this little 2x2 table right here to kind of help you understand how all of these different things that we do as data scientists fit into whether you're talking about past events or future events, or whether you're talking about simply observing the world as it comes to you, or whether you contemplate some kind of intervention, whether that's changing your own diet or changing the economy in some way. So some small to large. So let me just kind of describe each of these little cells of this table. And my goal here is not to try to be comprehensive at all about the techniques or ideas that you encounter in a data science major. It's just to get you excited and make you think this stuff is cool, because I think it's cool. I devote my life to this kind of stuff. And if you're setting out on this path, there's some chance that you will too. All right, so let's just take description. Here's a basic fact. I have 2 kids now. One is 3 and one is like 6 months old. And so I didn't know anything about being a father of a newborn. But one kind of weird fact that I learned when my first kid was being born was that there's actually a slight sex bias at birth in America. So 100 out of every 206 babies born in the United States are female. It's not exactly 50-50. There's no kind of biological or theoretical reason why it would be exactly 100 out of 206. That piece of information just comes from census data. You look at all of the births in the United States and you count up how many births there are, and you divide into that denominator how many of them are female, and you get about 100 out of 206. That's a really simple example of what I mean by description. Or how about this one? Here's a fact, a little more complex than that one, about Americans' musical tastes. So I claim that Americans' musical tastes are more diverse now than they were 20 years ago, when I guess it was like the tastes of my generation that were governing what were the top 40 hits. This is a conclusion that comes from simply describing data on the Billboard Top 100. And this is a data set that folks that take my class work with and kind of learn to do some very basic data wrangling skills with. How do you do that? What you do is you take every song since the beginning of the Billboard Top 100 back in, I don't know when that was, the 50s or the 60s or something like that. So you're talking 60, 70 years worth of data at this point. And you just count for every year how many unique songs in that year cracked the Billboard Top 100. And this is a little line graph. So like in 2001, when I was in college, if you want to date me, in terms of like when, how old I am, that was the absolute nadir of musical diversity in American taste at the top of the chart, because something like a little shy of 400 unique songs appeared in the Billboard Top 100 that year. And pretty much ever since then, it's been getting more diverse, to the point that, just a few years ago, which is, when this data set ends in 2020, 800, more than twice as many unique songs in the top 100. Okay, so really, really simple descriptive statistics, literally just counting, but at the end of the day, kind of an interesting sociological conclusion about what's happening to Americans' musical tastes. So these are just two examples. One's very simple, one's a little bit more complex, involving some actual coding skills and some kind of thinking and framing about questions involving this data set. But both, at the end of the day, are just describing the past, and there's kind of not much more to it than that. How about this one? Prediction. All right. So the claim, and this is a claim that I didn't take this out of nowhere. I took this off of Zillow, which is a website that many folks who are on the housing market, they're buying or selling, go to kind of understand what the housing market looks like in the area. Here's a picture of a house that I just cribbed off of Zillow. I went right to the middle of the country in St. Louis, Missouri. And the Zillow prediction was that this house would sell for just north of $420,000. Now, this house hasn't sold recently. So you might ask, like, where does that prediction come from? It's not that, oh, last month that whole house sold for $422,000. So this month we expect it would sell for about the same. This is a prediction that does come from data, but it's indirect, right? The way that it comes from data is by learning about some kind of relationship using other houses, about what kinds of things make houses more expensive, be it their size or the fact this is like a beautiful kind of old school brick house with cool attic eaves up here on a nice corner lot with landscaping. Like, how much do each of those features impact the price of a house in the St. Louis housing market? So that does very, very much come from data, that kind of prediction. And Zillow's secret sauce, to the extent that it's secret at all, entails figuring out how it is that you can extract those patterns from past sales data in order to make a prediction about what a new house, a new to you house is going to sell for. Okay. Here's another one, a little bit closer to home in terms of geographically for many people. This is data from ERCOT, which many of us who lived through the Texan power outages of 2021 will remember with some kind of bitterness. ERCOT is the grid operator in Texas, and it's very easy to scrape data from their website. So, like, for an example of prediction in my class, I went and did that, and I cross-referenced it with some weather data. And the thinking being here that let's say I want to forecast how much power is going to be demanded in the Gulf Coast region of Texas, which on the ERCOT grid is kind of basically from Galveston Bay to Matagorda Bay. I don't know, right? By definition, that's going to be this very, very, very complex function of everybody, turning on their lights, powering up Zoom on their computers to listen to info sessions, plugging in their Teslas, whatever it is, right? So it's a really, really complex phenomenon that's being measured here. But it's not entirely unpredictable. And kind of what the exercise that we do in the class that I teach is we take this observed past trends and like how much power is being demanded across the entire grid in that Gulf Coast region. And we try to correlate it with weather patterns, because a huge driver of demand for power, certainly in the Houston area, is how much people are using their air conditioners to make the temperature inside vaguely comfortable. And so that is an example, again, of using data indirectly to form a prediction about something that is literally unique. What's going to happen next Thursday in terms of power demand in Houston. And that is a really, really important theme of data science, is finding patterns in data in such a way that you can make predictions about one-off events. All right, so we've covered description, we've covered prediction. How about this next one? I'll call this causal inference. That's what it's called in the field. Causal meaning about cause and effect, and inference meaning trying to draw conclusions in the presence of uncertainty from data. So here's kind of just a random fact. If you look last month, gasoline prices went up by 5%. And overall consumption of gasoline went down by 4%. And that kind of makes sense, right? When gas prices go up, it tends to be people on the margin decide, well, I'm going to drive a little bit less or walk a little bit more, take the bus instead of drive. And so consumption of gas goes down. And therefore, you see this kind of inverse relationship between price and consumption. And economists could talk about that all the time. But in fact, if you ask economists what they would attribute that 4% to is a very complex mix of causes. They would say that about half of that reduction, 2% of that reduction, was actually caused by the increase in gasoline prices. And the other 2% was due to something else. Maybe it's seasonal patterns, things like weather, other things that drive demand for gasoline. So this is causal inference right here. It's trying to understand how much of some observed change in the world, like a 4% drop in consumption of gas, was due to some specific cause. So that we would call causes of effects. Here's a different one, right? This is actually the reverse. Instead of causes of effects, we have effects of causes. There's a large study in Spain that was published over a decade ago now, but it was very famous at the time, called the PREDIMED study. And what this study found was that eating a Mediterranean diet, and you can all Google what that means, but vegetables, fruit, fish, olive oil. This is the Google image search that I got when I searched for Mediterranean diet. You get a sense of what it entails. You eat a Mediterranean diet, according to the study, it cuts your risk of a heart attack by 1/3, which is not a trivial number right there. This actually comes from an experiment, and this kind of experiment can support inference about the effects of causes. In other words, you make an intervention by changing your diet. How's that going to change your health, in particular your risk, in this case, of a major cardiac event? And this type of causal inference always constitutes some kind of intervention in the world, whether it's a hypothetical intervention or an actual intervention, like, hey, I'm going to eat more olive oil. So causal inference kind of covers both, right? Effects of causes, causes of effects. And as you might guess from these kinds of examples, one in public health, one in economics, the applications of these ideas to other fields in other areas of our university are just immense. All right, now you might think that causal inference is one of those things, like you probably have heard this mantra about correlation not implying causality, but you would be surprised at how often people can mess this up, even people like publishing articles in reputable newspapers. Let's turn to, just for a quick aside here, to an epidemiologist called Ben Goldacre, who in some sense makes a living talking about this issue. I'll turn it over to him and let him talk.
An Australian study in 2001 found that olive oil in combination with fruits, vegetables and pulses offers measurable protection against skin wrinkling. So then they give the advice, if you eat olive oil and vegetables, you'll have fewer skin wrinkles. And they very helpfully tell you how to find the paper. So you go and find the paper, and what you find is an observational study, right? Obviously, nobody has ever been able to go back to like 1930, get all of the people born in one maternity unit, and half of them eat lots of fruit and veg and olive oil, and then half of them eat McDonald's, and then we see how many wrinkles you've got later. You have to take a snapshot of how people are now. And what you find is, of course, people who eat fruit and veg and olive oil have fewer skin wrinkles. But that's because people who eat fruit and veg and olive oil, they're freaks, okay? They're not normal. They're like you. They come to events like this, right? They are posh, they're wealthy, they're less likely to have outdoor jobs, they're less likely to do manual labor, they have better social support, they're less likely to smoke. So for a whole host of fascinating, interlocking social, political, and cultural reasons, they are less likely to have skin wrinkles. That doesn't mean that it's the vegetables or the olive oil.
All right, so there in a nutshell is why causal inference is hard, and it's I would say kind of one of the capstone ideas of how to do this well that you would learn in a statistics and data science major, something that runs right from the beginning of the freshman year all the way to the end of your senior year. Okay, so there you have it. Just a very high-level overview. We describe data sets, we make predictions from data sets, and we ask very, very difficult questions about what kinds of data sets can support judgments about cause and effect. The other kind of thing I wanted to talk about is now a little bit more of like, what types of concrete skills do you learn in your data science education? We've talked about ideas, we've talked about the kinds of problems we solve, where the rubber meets the road. How do you actually solve these problems? Well, I really like this data science Venn diagram that I'm showing you here. This is not my Venn diagram. This is one that has a lot of, I say, currency in the data science community. And you can see that data science sits right in the middle of this intersection of coding or computer science, of traditional statistics, and of domain-specific knowledge. And I'm going to talk a little bit about all of this. The domain-specific knowledge, Tommy will talk a little bit about that, and Jay as well, in terms of what we might call a breadth requirement in the SDS major. Again, more details later, but the gist of it is that it's important, if you want to learn about statistics and data science, that you learn about statistics and data science in the context of real problems with real data sets in another field. So that's the domain knowledge. What about the coding and the statistics? Well, let's take stats first. If you've taken a statistics class, or even if you haven't, and you kind of were asked to describe what statistics is, you might think of it as the science of measurement, of telling us what numbers can say in light of a data set about some particular question of interest. But I would say that statistics as a field is just about as much about measuring what you don't know as what you do know. And the idea here is that if you can talk about what you don't know in a data set, that's going to improve your understanding of a problem. And to drive that point home, I really like this old saying about watches. Okay. And here I don't mean like a smart watch or the watch that's on your phone that's connected to an atomic clock in Colorado or something like that. I mean like an old school watch that actually can make mistakes, right? So the saying goes like this: a person with one watch knows the time, but a person with two watches is never sure, because those two watches can differ. And I have no idea why it is that Ted Cruz, Princess Diana, and Diego Maradona are all wearing two watches in these photos, but that seems to be the only thing that unites them. In any event, why is it that two watches is actually useful and interesting and illustrates something about statistics here? It's because that we think it's actually better not to be sure in statistics, because if you've got two watches, not just one, you can talk about how the watches disagree with each other. And that allows you to say something about how precise your watches are. If your watches are always within a second of each other, then at least there's some kind of internal agreement about the time. Whereas if your watches disagree by 5 or 10 minutes, then that makes you distrust both watches more than if you just had one of those in isolation. The point is that with multiple measurements, you can say something not just about what you know, but you can say something about what you don't know, or the level of precision about your statements. And if you trust one watch, the statistician's perspective would be, okay, you may be certain, but it's a spurious certainty because you're also uninformed about the precision and accuracy of your measurements. And kind of thinking about those ideas from a mathematical perspective and kind of how those ideas impact scientific measurement is at the core of what it means to do statistics. So we learn tip to tail, kind of what it means to quantify our uncertainty about data in a statistics education. Then there's the coding. And coding, I think, there's often many reactions to the expectation that people will code in a major like statistics and data science. Some people are tremendously excited about learning to code. Some people already know how to code, and it's just a matter of kind of refining those edges. Some people have never seen any coding at all and come entirely without any background in computer science. And all of that is okay. My perspective here is to kind of excite you and get you motivated to code. Why would you want to code? I think there's so many reasons. Number one, I found that my journey becoming, and this happens to me every single day, right, of kind of learning to be a better coder and a more logical thinker, those goals are intertwined. The better I am at coding, the more experience I have solving very concrete logical problems. And you'll be so excited to see your journey as a logical thinker as you learn something like Python or R or any of the other languages that gain currency in data science these days. I think that there's another big virtue of learning to code, and it's intellectual self-sufficiency. And we're so used to trusting numbers that people quote to us, whether it's in a scientific paper or a reputable news article. The kind of intellectual self-sufficiency that you gain by learning to code is learning that you actually don't have to trust anyone in terms of what they say, that you can go to the data yourself and reproduce whatever analysis that somebody else has used to support their conclusions. And that is that self-sufficiency is a tremendous source of power and pride and confidence. And that's a big thing that we want to learn as data scientists. And then, of course, there's the very kind of direct reason to want to code, which is a lot of people want people who code on their staffs. It'll give you just directly career-ready data science skills. And at one point, Jay and Tommy and all the other folks kind of on behind the scenes here, we all try to kind of put together a bunch of logos of companies and institutions that hire people out of UT for their coding and data science skills. And eventually we just kind of stopped counting because this is where we got. So that's my take on why it is that you would want to be a statistics and data science major at UT, because you tackle fascinating questions, because you learn really valuable skills, whether it's statistical inference, whether it's coding, whether it's intellectual self-sufficiency, and there's just a tremendous amount of fun to be had. Now, I know that yeah, it's a good question. I mean, I think to some extent you'll see, it depends on what you mean by distribution, right? If you're talking about like, days of instruction, even that, if you've talked about something very measurable, it's very difficult to say because so much, I mean, like take a course that I teach, right? Where we learn a lot about statistical inference concepts. In order to do that, like we have to have our hands on a keyboard. And so do I count that as coding? Do I count that as statistical inference? It's very difficult to say. These things, I would encourage you not to think about those things as independent, but rather like, the woven strands of a basket, right? Where, okay, the strands are kind of interesting individually, but it's when you weave them together that they can support more than the sum of their parts. So it's a very difficult question to answer for sure. Like some of the classes will have a little bit more bias towards like statistical concepts or a little bit more bias towards hands on a keyboard. Let's mess with some data and learn some very concrete commands in R or Python for doing this or that. And I think Tomi would probably have a better answer in terms of how those courses break down when she actually goes through the curriculum. My kind of perspective on this is that it's difficult at a conceptual level to separate these two because what reason would you have to code if you didn't have a question involving data? And how would you actually solve the data problem if you didn't have the coding skills? So very, very difficult to decouple, I would say. Let me go to the chat. Yeah, it's hard to get a trend from one data point in terms of how things have changed. I feel like just my experience of teaching classes is that we all get better the second time around, right? And there's kind of always this 5 to 10% editing that happens every year in terms of like sharpening the example. So I don't think there's anything. I'm not aware of anything major that has changed in the major. It's more just a kind of sharper, more polished experience that comes from, we behind the lecterns getting a little bit more experience teaching this material to this crowd.
Okay. Another professor, Sally Ragsdale, and I both worked together to create the course that the students take in their very first semester as freshmen, so fall of their first year. Which contains a lot of things, but mainly teaches them R and kind of the concepts of data science. And so it was, we really had no idea what kinds of background students would be coming in with. So it was interesting to see that, we had some students who have been coding, not necessarily in R, but just coding in something since they were like in middle school. And then we had plenty of other people, about half the class who had never coded before. So it was an interesting challenge for us to, keep both sides of the spectrum kind of engaged the whole time, which I think we did do. But one thing that we are changing is that this is very specific, but just to give you an example. So we had one day on for loops. So teaching for loops in R, and we had one day on creating your own functions. And it turns out that I think we need more than one day of each of those things. So we might do 2 days of each of those with a lot more examples. So the content in the class is very similar, but there are certain things we're kind of taking out and adding back in based on what we learned from that first semester. We also, the last project, the final project of the class is for them to make an app, a Shiny app that is interactive. And one thing that I taught briefly at the end, but didn't require them to do for the project, was how to push it to the web and actually have it hosted for free. So some students did end up kind of doing it on their own, and they really liked like sending it to their parents and their family and friends to show them what they did in the class. But not everyone did it. And I really saw the value in people being able to push that to the web and share it. So that's something that, another example that I'll incorporate specifically in the class as part of the assignment, so they'll know how to do that.
That was a big part of, just background here, right? There's a huge part of the discussion of structuring this major was this is inherently a fast moving field, right? This is not English literature where, you're talking about things where things from 300-400 years ago are still relevant for study. It's something where, in our professional lives as researchers, we're on the preprint servers getting new papers like every week, trying to keep abreast of what's being done. And so trying to think about how to keep the major very live was a really important part. And part of that comes from being lean, not having a huge number of requirements and letting while having kind of the set of requirements that are that we view as absolutely crucial. If we were ever on the margin about something, it was more like, no, let's let that be an elective and let kind of the market for ideas drive what we're going to be teaching in 3 or 4 years' time, rather than set it down in stone. So the things that we've set down in stone in the catalog are very, very, I would say, core ideas and concepts. And then I expect to see some natural evolution in the elective portfolio. At the end of the day, it is a university. And so the pace of movement it's on a, kind of a yearly thing, right? It's not something we revise every month. But I would expect to see some pretty, if you're asking like at a 5-year snapshot, say, I would expect some pretty significant change in the elective portfolio for the very reason you cite. This is a very fast moving area. There's new ideas that right now are in the cutting edge of graduate level research that will very soon filter down to undergraduate. I mean, if you told me 2014 or something, when I first started reading papers about deep neural networks, that we would have a deep neural network that every undergraduate could log on to called ChatGPT that would, spit out answers. And that would be like a core part of many undergraduate courses. I would say that's pretty bold 10 years from now. And yet it's true, right? So having a structure in place that is lean and therefore adaptable was a big part of what we were trying to do with this major.
As Dr. Scott showcased, the statistics and data science consists of knowledge and skill sets that are relevant and in high demand in many industries. At UT, various departments have been offering statistics courses since the early 1910s, but it wasn't until 2007 that UT established the Division of Statistics and Scientific Computation. And then just 7 years later, in 2014, is when they created this new home for us, the Department of Statistics and Data Science that you know today. The growth of our department is aligned with the needs that we see in the world, and this new degree program that we launched in fall was crafted in a way to meet those needs specifically. So to give an overview of our degree requirements, it consists of 7 required courses in the major that students begin taking from the very first semester that they step foot on campus. We also have 5 foundational courses in mathematics and computer science, 4 courses for the breadth requirement, which I'll go into a little bit later, 2 courses of approved SDS electives, and 10 courses of free electives. And then the remainder of the hours are completed with the core curriculum courses. And all of that totals to 120 credit hours to complete the degree program. So there are a couple of items that I do want to highlight here. One of those is the breadth requirement. So this consists of 4 courses in a single field of study outside of SDS. This requirement was built into the program from the recognition that this discipline exists in an interdisciplinary realm, like Dr. Scott had mentioned. Statisticians and data scientists work in various fields. This breadth requirement is to ensure that our students are learning in depth about one area that they can complement the major studies with, and that hopefully it also aligns with the potential career goals that they have for themselves. And the other item that I want to highlight are the free electives. In the same vein of interdisciplinarity, these free electives provide maximum flexibility for our students to explore the application of statistics and data science through coursework offered by other units across campus. We want students to explore other disciplines that we have here at UT, which are very many. So taking all of that, this is just a suggested arrangement of courses, how a student with no college level credit through programs like advanced placement or dual credit might complete all of the degree requirements, all 120 hours within 4 years without taking any summer classes. So what you see here are all of the 120 hours in just the fall and spring semesters in 4 years. Those of you who are coming in with some college course credit will of course progress through the program with some adjustments. So some semesters might be a lighter course load, or you might choose to move some electives or core curriculum courses that you see listed in the 3rd or 4th year and move that earlier on, maybe in your 1st or 2nd year. And here I've highlighted the courses that are required for the major. They're also the foundational mathematics and computer science courses, and they generally need to be taken during the semester that they're listed there. Some of you who might be coming in with calculus credit, for example, your mathematics sequence of courses might move up by a semester, but we wouldn't want you to be taking those calculus courses in your 4th year, for example. Your computer science and mathematics courses are listed in that particular semester early on within the program because we want you to have that foundation. Every semester, you'll be meeting with an academic advisor and going over your individual circumstance of what courses you need to take to finish the degree and what sort of college level credit you already have. Those are things that'll come up in conversation with your academic advisor every semester when you meet with them. If you're a student who is expecting college level credit through exams, for example, so advanced placement exams, if you Google University of Texas testing services, you can look through all of the exam types that UT will accept, what sort of exam score you need to get, and what particular course credit that corresponds to. As far as other course credit you might be coming in with and how that fits into your particular degree plan, that's something that will be discussed with your academic advisor. The first opportunity for that is going to be during summer orientation. We recently made a decision to allow for our SCS majors to double major. There are stipulations to that. Students who are pursuing our SCS major have to be in good standing and be making satisfactory progress during their first year in order to be able to double major. That can be with any major on campus that allows for students to pretty much transfer into their program. So if a program on campus is allowing for transfers, that would be a major that would be available for students to pursue as a double major. That would effectively mean that you would be applying for transfer admission, internal transfer admission, and you would be keeping your current SCS major and adding on that secondary major to double major. As far as minors and what we have here at UT certificates, as far as those things go, those credentials are available to all of our majors. They can pursue minors or certificates. And courses that they take for those particular credentials can count towards either the breadth requirement if it's within the same field of study or towards the free electives. So if this question is referring to the science and technology core requirements, there's a list of courses that can fulfill the core curriculum requirements. So those chemistry courses are not the only ones that can count towards that.
Yeah, so the program definitely allows for that, and that's a great thing. Summer is kind of the ideal time to do that, and you could, in principle, do one every single summer during the program if you wanted. And I think that's a common thing to do over the summer, a good thing to do for lining up a job later.
You can use transfer credits to fulfill the free electives. You can even use exam credit to cover those free electives. I would not recommend claiming all of your exam credits in order to use towards elective hours early on in the program. The reason for that is that UT offers so many courses and so many different disciplines that you might want to take advantage of as a student here. Again, this program is interdisciplinary in nature. So while you can go ahead and claim those credits or use transfer credits to fulfill those elective hours, it may be beneficial for your growth as a student or whatever field you're wanting to go into once you finish this program to actually take those courses here at UT so that you have a fuller experience. If you would like to have a fuller experience and gain knowledge and potentially open more opportunities, taking certain classes and staying for the full 4 years may be beneficial. But if you have all of the specific required courses already completed and you want to go ahead and finish early and go ahead and claim those additional exam credits to take care of free electives, you're more than welcome to do that. There's nothing stopping a student from doing that. Of course, any discipline courses can count towards your free electives. There are no stipulations for the free electives. Now, computer science is a difficult area to secure seats in, depending on which course you're looking at. Computer science is a very popular discipline, but they do have the certificate for elements of computing that they have available. So I believe they do have some seats that are set aside for students who are pursuing that certificate to take certain CS courses. But CS major courses are not available to any students on campus except for CS majors. So that's something to keep in mind. Requirement. It can literally be any field of study on this campus, anything at all that's not SDS. So we do have 3 current SDS students. I wonder if any one or all 3 of you might have some ideas on what breadth requirement areas you guys are thinking about.
Yeah, I'm Caroline. And I am currently, like you said, I'm a freshman, obviously, and I'm currently thinking about doing my breadth requirement in education. So UT has like a really cool program where you can like get your teaching certificate, and I don't know, I'm looking into it. I haven't decided for sure, but I really want to find a way to combine my statistics and data science with education and kind of use that as like my career. So yeah.
I'm Kaya, so I'm kind of going a different route. I'm currently pursuing a business minor, and I've already started taking classes for that. So yeah, I guess unlike education, my thought has been more to take the data science into like the corporate world. So yeah.
Hi, I'm Victor, and I'm taking a lot of math classes right now. I'm hoping to get another degree in math, and I've just been taking courses this semester, last semester, and I think there are a lot of choices for the breadth requirement. I think I have also an art history course, so there are a lot of options for that.
So if a student decides that they want to double major and add a second major along with the SDS major, there's not any specific requirements that we would be setting in place for that. Meeting the requirements for the second major would be entirely dependent on what the course requirements are for that second major. In terms of applications, that would be something that students would have to contact or look online would be really the easiest option to see if there's a specific major that a student is interested in double majoring in. They should look at internal transfer information to see, one, if internal transfer is available for that particular major area. And if so, what does that application process look like for that area? There are some majors that are college or school dependent on their application, but there are some that are very specific to that major or that particular department. So doing some research ahead of time would be in your best interest if double majoring is something that you're interested in. But as I mentioned, starting that second or adding on that second major is something that students can do after their first year in the program with us at SDS. So last year, because it was the first year, we were shooting for a cohort of 50 students. This year, as we're going through the regular admissions process, we have increased that number. We're hoping for a target yield of somewhere between 100 to maybe 110 students. We won't know what our exact cohort size will look like until after the enrollment deposit deadline. In terms of teacher to student ratio, we try to keep that relatively low, especially during the first year in the program. This past fall semester, we had, for each of the first year SDS courses, we had 25 students maximum in each of those courses. For this upcoming fall semester, because we are increasing the cohort size, it's going to be close to double that. So we're looking at about 50 students per instructor for the first semester course. So currently, we do not offer a BSA option, an honors option for SDS specifically, but Polymath is an honors program that can be combined with the SDS program. What that degree plan looks like specifically for a student who is a polymath scholar will be discussed during orientation with the academic advisor, and that's specifically with the CNS Honors Office. Yes, anything that is within a single field of study can fulfill the breadth requirement. So if a student decides to pursue a minor or certificate program, those courses, as long as they're in a single field of study, those courses can count towards the breadth requirement. Some minors or certificates will require students to take courses in different fields of studies. If that's the case, those courses can count towards the free electives.
Tomi, it would be the CS courses that aren't part of the core courses for the SDS major, correct?
Yes.
Those are so excluding those courses. Yes.
Yes. Mm-hmm.
Yeah, so this was something I came in with no coding experience, and I was honestly really stressed about it and feeling very overwhelmed. Like I have to learn Python and like all these other languages over the summer, which is just like honestly really not the case. Even though like maybe to you guys it might have sounded a little cheesy, but this whole concept of like, you know, logical thinking with coding is actually really, really relevant. And since you guys chose this major, you're all obviously very STEM oriented and logical thinkers. And I think that as long as you put in the effort, like you guys will honestly be just fine. And like take it slow, you know, do the extra problems. It's worth it. Like you guys will be totally fine. And honestly, coming in with no experience has made the process even more rewarding. Like I feel so like this is like it sounds so cheesy, but it's actually true. I feel so like proud of myself when my code actually runs and all that stuff. So no, you guys will be fine. And it's honestly fun to learn it. And the professors are very, very helpful. And you have TAs and everything, like you have all the support. You'll be totally fine.
Even I also came in with no coding experience at all. And even after orientation, I didn't quite understand how much coding was going to be involved in this major. So like over the summer or in high school, like I didn't do any kind of coding, nothing to like prepare me because I didn't really realize. And then when I got here in the fall, it was way more coding than I was expecting. And kind of like Kai was saying, it was pretty stressful at first because I thought that it was expected of me to be able to code like perfectly. In the fall, mainly we used RStudio, and now we're doing like a lot of RStudio and Python. And every time I entered a new class where we were using a new language, like I was really stressed, and I'd be like, oh my gosh, like they expect me to know how to code perfectly. But that's not the case at all. The entire point is that you're learning. I had Professor Ragsdale in the fall, and she was very, very good at making sure that we understood that, you know, there was a learning curve to coding for sure. And yeah, you're not supposed to know how to do it perfectly. So if you have no experience, like don't stress about it. Don't worry about it all summer. You're going to come in and there are great resources here to help you whenever you need it, and you'll be just fine.
Yeah, I would say that I would go so far as to say some of my students who had the most coding experience, some of them actually struggled a lot because, you know, because they came in with so much, they kind of skipped classes or didn't really pay attention to some things, and then realized a little bit too late that we had gone over things that they didn't necessarily know. And so, I mean, they ended up fine, but the students who did not have any coding experience and were kind of freaked out in the beginning, but paid attention 100% in class and came to office hours and asked for help, they did really well. And like the students are saying, like after the first project, when they had to kind of put together their own report, I mean, you could see their faces. Like they were just so amazed that they made that whole project themselves and all the pictures and everything like from scratch, and they didn't know any coding before. So it was very rewarding for them. It was rewarding for us as teachers. And you know, professors don't even code perfectly. Nobody codes perfectly. So students would get really frustrated because they'd write all this code and then they'd get an error on like line 1 because they forgot a parentheses or like have an extra parentheses. Like that happens to me all the time. And I've been coding for I won't say how many years. But coding doesn't, like I was a freshman at UT, I got my undergrad here, and I was a computer science major at some point, and then switched to math. And partly that was because I felt like all of the my friends that were getting their majoring in computer science, like computer science was their major and it was also their hobby, and like coding was not my hobby, and I had no intention of coding becoming my hobby. And anyway, that's not the case in this major, and you don't need to know it before coming in. You will be there will be some moderate stress and anxiety probably in the first few weeks, but just know that you'll be okay. And Professor Ragsdale and I, like, we're prepared for that, and we're here to help you. So don't worry about that.
We currently don't have any other formal research opportunities set up yet because this program is so new. We don't have formal internship or mentorship programs with industry just yet. We don't have formal research opportunities set up just yet, but those are things that we are wanting to establish within the department. We're already having those talks internally. Currently, I'm not able to give a timeline for when that's going to happen or what sort of research opportunities there's going to be, but those are items that we are actively looking at within the department.
Right, I'm sort of thinking of James's slide that was crowded with the logos of all the companies that are hiring people with these sorts of skills. It's almost like what are the, it'd probably be easier to name the fields that aren't looking for people who are well versed in statistics and data science, and I can't even really think of one right now. I talk to students who are graduating, and I mean, they're not SDS majors, but they've taken statistics and data science courses, and they're looking at they're interviewing for careers in finance, in biotech, in tech, in a lot of them are using training in statistics as a good platform for going to grad school if they want to, for going to law school, for going to medical school. So yeah, really kind of the sky's the limit in all sorts of areas.
Question. So the core curriculum is effectively your general education courses that all undergraduate UT students have to take. That includes a first-year signature course that first-year students are expected to take. Most will take it during their first fall semester here at UT, but the topic in that one will vary greatly, and it's up to the students to decide which topics they want to take. But the first-year signature course is effectively a transition course to allow students to transition from their high school life into a college setting, specifically at UT. So we have a lot of these topics available for the first year signature course, so that students are selecting courses that are relevant to them, either in their personal life or things that are relevant politically, or if it's their interest or their career path or academic path they're looking at. So the topics vary in that one, but the other core curriculum courses that students will have to take include things like English composition. They have to take humanities course. There's a US and Texas government requirement, as well as a history requirement, social and behavioral sciences. There's also a natural science and technology requirement. Most of those courses for the natural science and technology are going to be covered by what's already required in the SDS curriculum. And then there's also a visual and performing arts requirement as well. So all of that makes up the 42-hour core curriculum that's required for all UT undergrads. So computer science, as I mentioned earlier, they're very restrictive in which courses non-majors can take. They are so restrictive that they have created, and because they're so popular, they've created a list of courses that are available to non-majors at UT. So if you were to Google computer science courses, non-majors. That should get you to the correct page because they get that question a lot, quite frequently from non-majors here at UT.
I think kind of like I mentioned earlier when talking about computer science, I don't know, I kind of went into it feeling overwhelmed already just based on my own assumptions that weren't necessarily true. And I think my advice would just to be like take it one step at a time. I feel like I went in being like I need to have my whole life planned out and know what I want my breadth requirement to be and internships and all that stuff. And that's really not the case. Like there's so many different things for you to try here to, you know, just figure everything out and like genuinely just take it one semester at a time. You're like the advisors will help you. They're knowledgeable and this, even though the major is new, they already like know so much and can help you. So yeah, just like don't stress yourself out too much. It's like you guys will be all good. And there's so many resources to help you figure everything out. So yeah.
And don't be afraid to go to office hours or ask your TAs any questions and your professors because they know a lot about this topic and they'll be able to help you.
Yeah, I was gonna say, like computer science is definitely not my passion. It's not my like favorite thing I've ever learned, but it is very cool to me that like I took my first computer science course this semester and I can write code and like read code and interpret code and whatever, all this stuff that I never could have imagined being able to do this time last year. Um, so yeah, I would just say it's okay if like computer science isn't like what you want to do because this isn't computer science. Um, and don't be those were definitely the courses I was the most scared of when I had to look at all the things that I had to do before I could like get my degree. The computer science courses definitely were the scariest to me, but like you can do it, you can get through it, even if it's not the thing that you're the most passionate about. So yeah.
We're excited to potentially, have you come and do this major. And if you have any questions that occur to you after this, don't hesitate to reach out to us. Email is usually the best, but don't be shy about doing that. And yeah, that's it. Hopefully we'll see you soon.